One of the ways to visualize and interact with the 3D digital models of reconstructed architecture is through virtual reality, commonly known as VR. The term VR refers to the real-time simulation of a digital scene that can be viewed through specific wearable electronic devices called headsets and interacted with particular controllers, gloves, or other advanced equipment. This type of experience allows users to virtually immerse in the scene, providing greater engagement and better perception of spaces and objects. Although the first experiments with this technology date back several decades ago, it's only recently that it started gaining traction in the field of architecture, thanks to the reduction in costs and increase in quality and computational capabilities of electronic devices. The initial commercial VR devices required sensors for motion tracking installed around the playing area, and needed the headset to be constantly connected via cable to a high-performance computer. The significant cost and limited practicality restricted their widespread adoption. Today, there are much more convenient all-in-one devices capable of operating in standalone or wireless modes. The rapid advancement in the development of these technological devices has led to the emergence of simple, affordable, and optimized software solutions. In addition to the numerous commercial sector-specific solutions, the two most popular and versatile platforms for developing VR applications are Unity and Unreal Engine, both of which can be downloaded for free. Despite the significant progress in recent years, these technologies still have limitations. Indeed, when used to visit reconstructed architectural spaces, special precautions must be taken. Reconstructive 3D models can be viewed through a VR headset in the form of pre-rendered 360 panoramic images, or through free navigations of virtual real-time rendered three-dimensional scenes. The former solution is easier to implement, as nearly all modern rendering software allows for the production of 360 panoramic images, while the latter requires specialized software and a more complex scene setup. These solutions offer different levels of interaction and have different potentials and challenges. 360 panoramic images can be of two types, monocular or stereoscopic. The first type describes an environment from all directions, relative to a single point of view. The second type, on the other hand, describes the environment from all directions relative to two centers of projection, spaced apart by interactional distance of a hypothetical observer. Producing a stereoscopic panoramic image requires more than simply rendering two monocular panoramic images from the projection centers placed at the observer's interocular distance. Instead, it's necessary to render the scene with a camera that implements a specific type of projection, called omnidirectional stereoscopic projection, which approximates stereoscopic vision in all directions. Most of the contemporary rendering applications include cameras capable of implementing this type of projection. Viewing a monocular panoramic image through a headset capable of tracking head rotations enhances immersion in the represented environment. However, space observed in this way may appear larger than normal due to the lack of stereoscopy. In contrast, viewing a stereoscopic panoramic image not only increases immersion, but also provides a better sense of depth and improved perception of the distance and size of surrounding objects. However, because the observer's position is predetermined, it's not possible to observe any motion parallax, which, upon moving the head, would make the retinal image of distant objects move slower than those of closer objects. To avoid a distorted interpretation of spaces due to the absence of motion parallax, it's essential to limit head translations when observing a panoramic image through a headset. The motion parallax effect can be accurately reproduced through interactive VR experiences, rendered in real time and viewed with the 6 degrees of freedom headsets, capable of tracking both rotations and translations in space. This solution currently offers the highest level of immersion and the best perception of depth, but does not solve all perceptual problems. Indeed, the invariance of the distance between the displays and the eyes prevent proper ocular accommodation. Accommodation refers to the visual systems process that allows focusing on objects at various distances. Our brain derives information related to the distance of the observed object by interpreting the effort that the eye muscles must exert to focus on it. This conflict between correct ocular vergence and incorrect accommodation can cause fatigue in some users and is currently unresolved in all commercial headsets. VR experiences can also cause motion sickness in some users more than others, which can be reduced with training or through software or hardware adjustments. Regarding software adjustments, it is sufficient to follow some well-known best practices during the development of VR applications. Instead, for hardware adjustments, when choosing a headset, attention must be paid to various parameters such as interpupillary distance, angular resolution, field of view, refresh rate, and other technical features like display brightness and ergonomics. Finally, it's important to remember that preparing a 3D model for real-time interactive VR experiences with 6 degrees of freedom requires optimization in terms of polygon count, texture resolution, material complexity, and shading. This need arises because to display a scene in real time, the hardware must perform a larger number of calculations very quickly, and the two displays integrated into the headset require a much higher resolution than that of a traditional monitor. In conclusion, as of now, pre-rendered 360 panoramic images are easier to create and more suitable for producing photorealistic views, as the computation is not done in real time, and the reconstructive model does not require specific optimizations. But the trade-off is the limited interaction to only 3 degrees of freedom and a poorer perception of distances and spaces. On the other hand, an interactive experience explorable in real time with 6 degrees of freedom provide better immersion and perception of distances and spaces. However, the trade-off is a reduced level of photorealism, a more complex optimization of the models, and greater storage space required for archiving and sharing the VR experience.